Good morning, everyone, and thanks so much for joining the Clallam County Coffee Economic Development Council Coffee Chat. We are excited to hear from Harold Tobin today. He's the author of the Cascadia Subduction Zone paper, and he's also a professor and Harris Endowed Chair in Seismology and Geohazards. He's the director of Pacific Northwest Seismic Network Department of Earth and Space Sciences at the University of Washington. And so just before Harold takes it, a few housekeeping items. We request that you put yourself on mute so we don't inadvertently pick up any background noises and that will disrupt the presentation. And then if you have any questions, we like this to be fairly interactive. So if you'll either put your question in the chat if you'd like me to ask it of Harold, or if you prefer to ask it yourself, you're certainly welcome to do that. And you can raise your hand, electronic hand, and we will call on you. So with that, Harold, thanks once again for joining us. We really appreciate it. We're obviously all really interested in this subject. And go ahead and take it away.
All right. Well, good morning, everybody. Thank you so much. I really appreciate the opportunity to talk to you. I've got a little bit of a presentation put together that'll touch on a range of topics from sort of how do we know we have earthquake hazard and what is it? Then down to some more details about Cascadia Subduction Zone and the other faults that are potential earthquake hazards. So let me share these slides with you. And let's see, get that into full screen mode. Oh, maybe I have the wrong one going. Is that looking good? You see the full
Yes,
screen
that
slide?
does. That looks great.
And
Perfect.
now I don't have the floating image, so I may be able to see the chat, but just again, let me know if there's something that comes up that you want me to stop and pause for a second on. Yeah, okay. So as you said, I'm a professor at UW, and I work kind of across the boundary between seismology and geology, actually. This photo, very geological, high in the Olympics. We'll come back around towards the end of my presentation here, and I'll tell you why this relates back to earthquakes, even in this sort of alpine zone of the Olympics up underneath the White Glacier there. But first, what I'm going to do is step back and really talk about earthquakes in our region a little bit more broadly, and how, what the nature of our hazard is and how we know about it and how it compares to maybe other places as well. I mean, one thing to say just really broadly is earthquakes happen all the time around the world, right? I think people think of them as rare events because the ones we hear about are the ones that are damaging and larger. But picking magnitude 4.5, which we haven't had a lot of in our region, in recent years, happen all over the planet, right? This is a week. This is just the past week. I grabbed this screenshot last night. So earthquakes are going on all the time. Obviously, as you can also see, they're not just sort of random on the planet, but they're spread in specific areas. And the rim of the Pacific, the so-called Ring of Fire, which the name derives more from the volcanoes maybe than the earthquakes, but it's a place where we have all of these places where two plate tectonic plates meet. And that's where an awful lot of the earthquakes are concentrated. You can really see that, I think, vividly in this image, and some other places too. Turkey, where we know there was a big earthquake, I'll talk briefly about last year, and then the Himalayas and other places of where the plates are in motion and they're converging and colliding with each other. So earthquakes happen all the time. But of course, they don't happen in any one place very often at all. In fact, sometimes, decades to centuries apart for big or damaging ones. So using kind of the whole historic record and everything we know about the hazard from faults that maybe we don't have a historic record of, the U.S. Geological Survey and a sort of panels of experts have put together things like this map. This is what's actually called the U.S. National Seismic Hazard Model, NSHM, and it's a recent update of it from 2024. And it just has a kind of a color coding here of the chance of damaging shaking in the next 100 years. So it's a pretty, broad definition. And You can see there are some bullseyes like around this area in Missouri. The New Madrid Fault Zone, where way back in the 1800s, there were clearly some pretty large earthquakes that affected the Mississippi River region. But the hazard is largely concentrated along the plate boundaries, the West Coast. California shows the most red, not surprisingly, along the San Andreas Fault and other faults that are related. And the Pacific Northwest has the other big concentration, right? Unfortunately, right on top of us is the other sort of big patch of red on this map. The other thing that's plotted on here, I should say before I move on from this slide, is the population density, right? So that's what these, the colored dots are, and just showing that, unfortunately, for the West Coast, the earthquake hazard really converges with where people live. People live in the Los Angeles Basin in large concentrations, San Francisco Bay Area, and the Puget Sound. And guess what? All three are places of high earthquake hazard. It's kind of another story, but interestingly, that's not completely coincidental. The existence of the lowlands that create places where people like to live and big ports and harbors is also related to plate tectonics and the faults that that make the earthquakes. But so if we zoom in on our region, that's the problem, right? The regional hazard coincides with the major population center. You can see that it's not even clearly
Today
just
is
all right. Not even just the offshore big one fault. We'll talk about the Cascadia subduction zone. That creates a lot of the hazard, but then there's an extra sort of added on layer of hazard in the Puget Sound region and extending obviously into the peninsula as well. And so I'll kind of, I'll talk about some of the faults that create our hazards here, the different sources of hazard as I go along. But we haven't really had a lot of big felt earthquakes. I don't know if anybody, probably where some of you guys are, felt the earthquake that was centered kind of between San Juan Island and Victoria last week. I think it ended up as a 4.0 or so. That's actually the largest earthquake we've had in the populated areas of Washington all year, I think. But we do record earthquakes all the time. This is another map I just grabbed last night. It was just October 1 to October 1 of the past 12 months. And we see a lot of earthquakes in our region. Every dot on there is an earthquake that the Pacific Northwest Seismic Network has recorded. Notice that the magnitudes get really small. I mean, we only feel earthquakes when they're above at least about 3, very rarely 2.8 or 2.9 or something like that. Fortunately, there's no big circles on the map. The damaging ones really start kind of with magnitude 6, maybe in, again, some cases a little bit smaller. But we have a lot of magnitude 2, 1 and 2 level earthquakes, mostly not felt by people, mostly just picked up by our instruments. And you can kind of see there's a pattern in them, right? So part of the reason why our hazard is concentrated is because our small earthquakes are concentrated in the Puget Sound region. Look at this cluster, and any year I showed you would look similar. Oregon is mostly free of even smaller earthquakes, and Washington has a lot of them. And so that's one piece of the hazard, is just saying, well, where we see smaller earthquakes, we may see bigger earthquakes. But that's not the whole story at all, for a couple of different reasons. And one is just that you need bigger faults to make bigger earthquakes. And you also, you have faults that sometimes are so locked up and stuck and not slipping that they're really quiet. And that's the sort of ominous quiet we talk about for the offshore Cascadia subduction zone. And I'll come back around to that in just a minute. But, so we have small scale seismicity. We saw the hazard map. We have hazard that is not as high as California, but sort of comparable. But, again, very few, when I asked my undergrads who are, 18, 19, 20 years old, if they've felt an earthquake in their lives, only a few of them raise their hands, and often they're from out of state, and maybe a few from around Western Washington. So in the past decade or two, it's been pretty quiet, right? But here's a question. What was the most damaging earthquake in terms of economic cost in the US in the past 25 years? If you stop and think about it, maybe Ridgecrest in California or an Alaska earthquake or something like that. But I've kind of telegraphed the answer already. So if you're thinking to yourself, California, no, it's actually Nisqually, right? It's the 2001 earthquake that shook our whole region, centered just north of Olympia, caused somewhere, total losses well over $1 billion. These are insured losses, which is easier to count. And you can see these other ones are just longer than 25 years ago. So that's a kind of a measure that we have this high earthquake hazard, but fairly infrequent or rare events, earthquakes. So that translates into, FEMA's map of earthquake losses and the expected cost. And what they do is they do this as an annualized version of the loss. So obviously big earthquakes come very rarely, decades apart, but when they do, they're expensive. They're big disasters. And second only to California in the USA, above Alaska, above, Utah or Nevada, et cetera, all the other places you might think of, even Puerto Rico and Hawaii. The annualized cost of earthquakes in Washington state alone is well over $1 billion based on potential property losses, based on the experience of the Nisqually quake, and so on. So that's the source of concern, but also the motivation for spending money on mitigation and all of the things that we do. Okay, Nisqually was in 2001. We haven't had a really significant earthquake, a large earthquake in Washington since then. Everybody knows California is sitting there thinking about big ones along the San Andreas Fault, and yet hasn't seen a lot since the Northridge earthquake back in the 1990s and the Loma Prieta in 1989. So we have to figure out ways to characterize that hazard. How often do these earthquakes occur over and over again, or how much time goes on between them? And so there's a lot of science that's going into trying to understand how much hazard any given fault or any different earthquake scenario really presents. And our historical record isn't very long, right? We only have records that people have kept, written records for, less than about 200 years in our region. And the indigenous folks here have oral histories that clearly refer to earthquakes, tsunamis, things I think people have heard about. Those things, but they don't tend to give us the kind of information we can use to make calculations of recurrence intervals for clear reasons. Well, one thing we can do is we can look at the type of earthquake that Nisqually was and say, okay, this is actually a repeat of very similar earthquakes seismologically that have happened before. So there's 2001, but in 1965, there was a very similar magnitude earthquake. MW is just shorthand for magnitude to seismologists. So about a 6.7 in 65 and a similar sized earthquake in 1949, all of them centered somewhere between Olympia and Seattle. And all of them sharing the same characteristic I'll show you in a few minutes of being these relatively deep earthquakes. And all of them caused damage. We're not losing as many lives anymore, fortunately. 2001 didn't kill anybody, or I should say one person died of a heart attack related clearly to the earthquake, but no injury damage, injury deaths came out of this one, but a lot of damage. And, we've all seen images of the Nisqually damage, like in downtown Seattle in Pioneer Square. It got the attention of our legislature because it did a lot of damage to the state capitol and the region around it, and so on. So that's one type of earthquake that we have around here. And what I'll spend a couple minutes on now is really kind of outlining for you 3 different types of earthquakes that generate our seismic hazard and the reason for that bullseye in our region in that hazard map. Okay. So the first one I want to talk about are the ones that are like Nisqually, these ones we call deep slab earthquakes. Why slab? Well, that's sort of geoterminology. You guys know that we live along this thing called a subduction zone. Everybody's kind of heard at this point about the Cascadia Subduction zone, and that it's the place where the seafloor plate, okay, so the Earth's tectonic plate offshore called Juan de Fuca, is literally sliding underneath Western North America, and the land we all stand on is sliding like a wedge, like a kind of a doorstop sliding out over the floor of this Juan de Fuca plate. We'll get to the offshore subduction zone in a minute, but in the meantime, earthquakes like Nisqually actually are also part of the subduction zone, but they happen way down here at about 40 or 50 miles below our feet. So below your feet, below my feet here in Seattle. If you go straight down, you go through North America, but eventually, from a plate tectonic standpoint, you actually get to the former bottom of the ocean. You get to the Juan de Fuca plate when you get down into there. And within that plate are these deep earthquakes. We don't think they're likely to be much larger than magnitude 7, but we don't really know that for a fact. It's possible that these could get above magnitude 7. Our experience of them is this magnitude range. But because 3 of them happened in basically the 20th century or up through 2001, we kind of have to assume that that's about what the average recurrence time is. So it's about, between 20 and 30 years. Well, it's been 23 years since that one. So we're basically in a time frame where there's no reason to not think that another Nisqually could happen more or less at any time. But certainly if it didn't happen for a decade or two, that wouldn't be surprising, or longer. At any rate, what that means is we assign it and kind of go through a formal kind of probability calculation, 85% chance of another one happening in the next 50 years. Not 50 years from now, just sometime in the next 50 years, whether it's tomorrow or, towards the 2080s, that another Nisqually would take place, or one like it. And of course, it could be closer to Seattle. It could be further out the peninsula. There's different places where they can occur, although so far they seem to cluster at a particular depth. Okay, so that's the most likely next earthquake, large earthquake that any of us would be likely to feel. And that's certainly, we need to be prepared for. Now, obviously, the one people want to hear about and want to talk about all the time is the so-called really big one, right? The offshore Cascadia Subduction fault. The potential for this entire system out here to be a locked fault zone that would generate a much, much larger earthquake on a massive scale. And so if we look at this, I said that the two plates meet in this zone in here. Well, it turns out that some of this is so deep that it only generates these relatively smaller earthquakes, and the rest kind of moves like taffy flowing. It's what we call ductile rocks, or ones that can't support the stress because they're so hot that builds up to form an earthquake. But up here, mostly offshore, coming onshore, unfortunately for you guys, mostly only underneath Western Washington, the Olympic Peninsula regime, is a part we call the locked zone. It's a patch where the temperature at the boundary between the two plates is low enough that we think they get stuck together, and for centuries, literally, they've been building up stress. And so this thing I just highlighted is the whole fault running all the way from Vancouver Island down to Northern California that represents that Cascadia subduction zone and is the potential source for a magnitude 9 class earthquake, right? One of the largest kinds of earthquakes we can have on the planet, similar in scale and scope and tsunami generating potential, as you've heard before, to the Japan 2011 disaster that took place off northern Japan. So, okay, we've known since maybe the late 1980s, early 1990s, that it appeared that this subduction zone really could produce earthquakes. But, we haven't seen one, right? We haven't had one that's occurred in historic times. We don't have any direct experience of a Cascadia subduction zone mega earthquake. So we have to turn to other means of knowing about them. And maybe you've heard some of this story before. I'll just briefly touch on that. Really shows that there genuinely was one, certainly off Washington and Northern Oregon, and maybe extending as far south as Northern California, as one very, very large earthquake over a huge region, hundreds of miles long, that generated a tsunami. And that it was exactly in the year 1700, 324 years ago. We know that from this amazing story of geological sleuthing that took in, tree ring dating of the ghost forests along the estuaries of the coast, like in the Grays Harbor region, Copalis River and other places. I think this photo is Copalis River. That all of these trees died in the same year, coupled with recognition of historical records from all the way across the ocean in Japan that a tsunami with no earthquake happened over there, the so-called orphan tsunami. And there's this great book, which I recommend people get. You can actually download it for free from the USGS, called The Orphan Tsunami of 1700 by Brian Atwater and Kenji Satake and some other people. So that really nailed down the date of that last earthquake and showed that its magnitude had to be big enough to send, this is a computer model, to send the tsunami all the way over to Japan, and nailed it down right to the literal time of day. at night, January 26, 1700. And it had to be in this range of magnitudes. This is how we know that magnitude for the last Cascadia subduction zone event. We also have these offshore deposits of sediments that were giant, basically underwater landslides. We call them turbidites because they're turbidity currents of water. No, not important, the name. But those deposits in the sediments, when people can go out and take sediment cores of them in the ocean off our coast, have shown that there's repeated events that look like synchronous landslides generated by earthquakes repeatedly over the past 10,000 years. This is actually a 10,000 year kind of each of the big fat sticks is one of the large earthquakes that we think we know about with radiocarbon dating to tell you when they are. So we're sitting here 324 years since the last one. Some of them are relatively close together in time, like 200 years or less. Other ones go as much as 800 years apart. It all comes together to say there's an average, just an average, not a lockstep metronome of 450 to about 500-year interval between those earthquakes. Okay, so that's a story we've known for a little while. Actually, it was recently corroborated in a really spectacular fashion by a new study that just came out from the US Geological Survey. It was published only a month or two ago. And what they've done is they've gone out to Ozette Lake, okay, on the peninsula. And Ozette Lake preserves an amazing record in the mud at the bottom of the lake, in the sediments that are layered down there, of the same kinds of landslide deposits, the same kinds of sediment layers that are signatures of earthquakes. Here's a map of the lake, and this is all the crisscrossing lines that they took a boat and mapped out. They actually did like a echo sounder profile, except one that penetrates down into the sediments so you can see the individual layers. And in fact, that's what these colored stripes are across this picture over here on this side. And then in many places along all of those, studied, mapped out track lines with the boat, they also took sediment cores. And each of these dots is a sediment core, and they put together a story of these deposits. And I'll spare you all the technical details, but basically what it says is that for the last 5,000 years, and probably for the last 14,000 years, although the cores don't go that deep, it confirms this average time. So we're really learning this stuff. Remember, these are not things that we just know. They have to be revealed to us by these very, complex and in some ways subtle ways to study what's going on below the bottom of the sea in, miles deep water, or in this remote lake location that you have to get out there and actually figure out what the stratigraphy of the lake is and everything else. But they've done this really good work, and I think it's superb. So that's really telling us that that average time between the big ones is huge. I guess before I move on, I'll just say too, 324 years since the last one, but about this average time between the big ones is where we come up with this number of 15% probability in 50 over the next 50 years. Okay, so less than even odds that this will happen in the next 50 years, but not a very small probability, still a significant chance. The 25% part of this comes mostly from Northern California and Southern Oregon, where there's some evidence that they're more frequent, but smaller, if smaller means magnitude 8 instead of 9. Turns out that's a big difference. I like to put it in perspective. We all know about the really big one story. This is the almost 10 years old, 9 years old now, New Yorker article that caused a lot of attention. And we have, I think, a feeling that when one of these earthquakes happens, well, first of all, we know it'll be really large. And just the perspective that this is the Alaska 9.2, probably comparable sized earthquake, maybe even a little bit bigger than what Cascadia would be. This pie chart is just the Alaska earthquake over here in terms of how much magnitude, how much energy was released by the earthquake, how strong was the shaking and everything else. 70 times larger than all the earthquakes in the rest of the USA since 1964, in the last 60 years. That includes Nisqually, that includes all the California earthquakes since then, Utah earthquakes, et cetera. Everything west of the Rockies is just this little sliver right here. Some other big Alaska quakes, are this other quarter or so sitting over here. So we've seen what a magnitude 9 earthquake is like, and it was a terrible earthquake. It did some real damage, mostly affected a not very populated area, so that's good. Loss of life was not large. But we also know some other things about it, like that what the shaking is actually like for these earthquakes and what the tsunami impacts are. And we saw that in Japan. So, this article generated, I think, a lot of attention, but also maybe a lot of consternation or just fear, I think, because of things like this quote, right? We're planning as if everything west of I-5 will be toast. Everybody heard that quote at the time. And what it really means is not that everything will be toast, because it won't be. We've seen magnitude 9 earthquakes around the planet. We know what they look like. It will cause widespread damage and very real damage. And in the tsunami inundation zone, that's very serious. If you're in the inundation zone, you need to have a place to, escape to, or chance of losing your life is very high. Damage to property is also potentially very high, but it doesn't mean, for example, that every bridge will fall down. It means every bridge has a chance of falling down, and probably, there's different numbers for different areas, but I can just throw some out. It's sort of the 10%, 5%, 20% may be unserviceable, depending on where you are, 40 or 50% maybe. We've seen what happened in North Carolina just now. Big disasters with widespread regional effects have a lot to overwhelm people in the aftermath, and getting basic services up and running and everything is something we're just beginning to see play out in North Carolina. And you guys know better than I do, in fact, what it will take to do a lot of those things in the region. But I want to emphasize too that the estimates of, casualties from our magnitude 9 scale earthquake are in the range of tens of thousands of people. That's a terrible number. But there are hundreds of thousands to even millions of people in the impacted zone overall. So I sometimes get the sense that people will throw up their hands and say, we can't do anything to survive this, so why prepare? And I think that's the wrong response. Most of us are very much likely to survive it, and need to think about what's our resilience so that we can pick the pieces back up quickly and get society functioning again after a big event like this takes place. Okay, I'll talk a little bit more about the big ones in a little while, but there is a third type of earthquake sources that we have to think about, and you may also be aware of these, but we have these faults that are up in the North American plate. We call them the shallow still meaning a few miles below our feet, but in the upper, let's say 10 or 15 miles of the crust, and they're in North America. They're not even in the subduction zone, although they exist kind of because of the stresses ultimately of the two plates colliding with each other. But we have a number of those faults, and we have, the one over here on the other side of the mountains, actually in 1872, probably our largest historic earthquake in Washington. But a bunch of these faults that haven't shown us a historic earthquake, but look like they have high hazard. And so this is probably the least well understood number here, but about a 15% probability is also kind of assigned to those faults. We zoom in on our region. Each one of these lines on this map is one of these faults, most of which we know about not from historic earthquakes, because we haven't seen one in the past 150 years, but on geologic records, again, of how they are, what evidence they show for sudden breaks and things like liquefaction around them and other changes to the landscape that can be identified for these different faults. And there are a bunch of them. I'm going to highlight in a second the Saddle Hill Fault and Seattle Fault, but I should probably mention the Lake Creek, Boundary Creek Fault, which runs through the Lake Crescent region. It's in your turf, and there's been some recent attention to this fault. It's a slow-moving fault that's not accumulating stress and strain very, very rapidly. In some ways, these are the hardest type to put a number on and characterize, because they probably can have earthquakes as big as something like magnitude 7. That's the bad news. But they also almost certainly only have those earthquakes every few thousand years, to even on the scale of 5 to 10,000 years apart. based again on what they can see from geologic study of these faults. And so the events are rare but hazardous. It's the ultimate sort of black swan from the perspective of the coast of the straits. And this map, this map is obviously USA centric. These faults actually continue across southern Vancouver Island. The Leech River Fault is this. You can even see it in the topography. This line right in here that connects the dots between those ones and those ones. And that fault also has similar magnitude potential to affect Victoria, but also, the seismic waves go through the earth, not the water. So your side of the straits as well. All right, well, let me just touch on the Seattle Fault and the Saddle Hill Fault, which is the one running through just south of downtown Seattle, kind of Sodo area. And then this is the Saddle Mountain Fault, Saddle Hill Fault over here. I think it has more than one name. There was a recent study just came out late last year that was doing the same sort of thing, using tree rings, in this case from these fallen logs in ponds and lakes that literally with underwater chainsaw work, amazing work by the folks who did this study, found that there was strong evidence that the last earthquake on the Seattle Fault was in the year 923 AD with great dendrochronology, tree rings. And the last earthquake on the Saddle Mountain Fault was also in the year 923. In fact, we're both in the winter of 923 AD, sometime between two growing seasons. Well, that leaves the potential that this is either two earthquakes or one earthquake, and we don't know the answer, but there's no reason why they couldn't connect up. So the problem is that the evidence suggests that there's the potential for a 7.5 earthquake on the Seattle Fault and a 7.3 or so on the Saddle Mountain Fault. And if you combine them, it's an even larger earthquake. And if those numbers seem, oh, they're close together, remember, this is all a logarithmic scale. A 7.8 is twice as big an earthquake as a 7.5, approximately. So, the potential for a large earthquake that spans the Southern Peninsula through Seattle is real. Now, again, their work also suggested no other earthquake of this magnitude happened in the several thousand years prior to that event. So it's kind of this black swan situation. But one thing we did was we looked at the scale of the length of these faults and some of the other faults on the map. And last year, I compared them to what happened in Turkey in February 2023. And the map down here is all of our faults in the Seattle Times, but I've just overlaid on it the actual faults, the two faults that ruptured, that caused the earthquakes in Turkey last year. And the scale and the size and the types of faults are all very similar and running through a populated urban region. So the yellow lines are just me plopping the Turkish faults down on top of our faults as a comparison. So we wrote an op-ed piece actually in the Seattle Times with some of my structural engineering colleagues at UW to just say, look, we don't have a built environment that is as vulnerable as in southern Turkey, but if we think we're ready, we're not. We're better prepared than we were at the time of Nisqually. But we have lots and lots of work to do all across our region, not just in the urbanized areas, to be prepared. Good news for people in non-urban areas is that, low 1 or 2 story, 3-story wood frame buildings and houses are some of the best structures to live in from the point of view of earthquakes. Unfortunately, we still have thousands, actually about 1,000 just in Seattle, but many thousands across the state, and certainly including in your communities, of unreinforced masonry buildings called URMs. Also older concrete buildings that don't have enough steel rebar in them. Those are just generically called non-ductile concrete, ones that will crumble rather than bend and flex during earthquakes. And in our whole region, including in the city, we really, including all the new skyscrapers going up in Seattle, we don't have what are called base isolated buildings, buildings with shock absorbers built into the foundations that can take some of the seismic shaking. They're starting to build those more in California. They build thousands of them in the cities in Japan or Taiwan or some other areas with a lot of earthquake hazard across the ocean. We have, as you guys know, hundreds of school buildings that are either in the tsunami inundation zone or have been given Fs for risk of partial or complete collapse during big earthquakes. The legislature addressed this last year, or in the last round, with a sort of first slug of $140 million to work on those buildings. Clallam County was actually instrumental in getting that funding to happen. But it's a multi-billion-dollar problem that we're just going to have to keep working on over time. And then I think this powerlessness that I referred to earlier is a factor. You know, people are afraid of earthquakes. And we have uncertainties. And it's partly that our experience is lacking. You know, you might remember there was this earthquake that affected New York City last spring, made the news quite a lot, magnitude 4.8. There's the earthquake's location in New Jersey. Here's a map of who felt it. This is the response of all the people who filled out those "Did you feel it" things on the USGS. Goes all the way to north of Boston and down to Washington, D.C. Millions and millions of Americans felt that earthquake. We haven't had a magnitude 4.8 in Washington since just after Nisqually 20 years ago. So we don't have that same experience. We have this problem that we have very real earthquake hazard, but we don't actually have a lot of experience with earthquakes. So we have to do things to try to understand that and address that and keep them in people's minds. So I'm from the Pacific Northwest Seismic Network, among other hats that I wear, and we operate seismometers all over the state to detect earthquakes. I'll just show you a better map in just a second. The data from every instrument we operate streams into our computers at UW, and they're working 24/7, and we're actually running automatic algorithms that can detect earthquakes before a person is involved at all and determine whether it's big enough for an earthquake early warning. I'll show you that in a second, within a few seconds before the shaking even reaches most people who might feel it. We're part of a national network, but we're responsible for the US's seismological instruments for all of Washington and Oregon and this whole region at the PNSN run out of UW. So we have seismometers. Here's what some of them might look like. We've got one literally next to the Space Needle at Seattle Center. We've got them over in the Yakima Valley. We've got one seismometer that's at the Snow Dome right next to Mount Olympus, next to the old hut that's up there for glacier research originally. We're operating seismometers and sending with radio waves the signals from them down so that they're part of that giant network. We've grown our network enormously recently with partnership with the U.S. Geological Survey. This is 2018. All the pink things in various shapes are our stations over that time. At that time, we had 229. Here's 2023. We have 545. Actually, that's the wrong number now. It's closer to 700 stations. And what you can see is we've densified the network specifically along the coast quite a lot. And I'll just go back and forth. And the reasons for that is to have a network dense enough to do a much better job of detecting the events that start offshore. We want to be able to know that we know exactly what's happening both in the in-between times before an earthquake, because maybe those small earthquakes are a clue to us to understand the science of what may be happening building up towards an earthquake. And secondly, so that we have the best possible earthquake early warning for an event that starts out here and we detect it, you know, along the coast. And all of this is to go into the earthquake early warning system, right? So I'll skip a little video I had here. Probably they don't play very well on Zoom anyway. But you know, earthquakes are inevitable. So certainly we need resilient construction, some of the stuff you guys were talking about right before the meeting, and how we deal with that, getting people out of harm's way, life safety, whether it's tsunami evacuation or simple things like drop, hold on. And one tool we bring to it now is earthquake early warning with this ShakeAlert system. So ShakeAlert is the thing that can alert you to your mobile phone. It went live in 2021. The only actual delivery of ShakeAlert, because the threshold is magnitude 5 and a shaking intensity that we call level 4, in order for a ShakeAlert to actually go out to everyone, the only alert we've had is for one of those far offshore events where a little bit of your county, mostly around Nia Bay and down to La Push, received or could have received an alert via the system. Actually, I think through the MyShake app specifically. So very few people were actually alerted. This says no alerts delivered yet. That's because it's nearly completely true. And that was the first one just this summer. We haven't had in the populated areas a big alert event. But we can expect, you know, that this will take place sooner or later. There have been a number and very successful ones in California where people got the alerts before they felt the shaking, maybe only 5 to 10 seconds before, but that's enough time to mentally prepare yourself and not panic. We've seen in earthquakes that people have a tendency to panic and run when they just feel shaking. When they get the alert, instead, they do things like freeze and stop and think, oh, what am I supposed to do? And that can happen in amazingly few seconds and actually reduces injuries. And it's been shown to in Taiwan and Japan, and now beginning to be shown in California as well, that those are really positive effects of earthquake early warning. We also have technical partners who use the earthquake early warning, not just in sense of a mobile phone alert, but to do important things like triggering the PA system in schools. It's beginning to happen. We have a number of schools. Stanwood Camino is one. So is the school in Westport. Oh shoot, the name is escaping me right at this moment, but has now implemented ShakeAlert earthquake early warning for the PAs in the school. We would love any school district to talk to us. This is very inexpensive, and PNSN will actually float the initial costs for the early adopters right now. Allen Institute for Brain Science is using it to protect all their delicate lab operations. The BART trains in the Bay Area, we would love for that to happen with light rail around here. We're not quite there yet. Stop the trains and so on. So all these things happen. Okay, I've already talked about the seismic safety in schools, so I don't want to, I'm already overshooting my time, but I just have a few more things to touch on, and I would love to spend a few more minutes on them if that's all right. Somebody shout at me if it's not. We're working to understand the hazard better. So I'll step away from just the seismology of it all to talk about the things we're doing both to study the hazard and to work with communities. Two big initiatives I'm involved in, and we at UW are involved in, is the Cascadia COPES Hub, Coastlines and People Hazards Research Hub, which both does the science of what are the hazards, but also the how can we help communities build resilience. That's the thing I was referring to before we started with Dan Abramson as one of my collaborators at UW, working directly with communities. This is a community meeting in Westport to talk about the tsunami evacuation planning and mitigation strategies for building better abilities to evacuate, including talking about more of the vertical evacuation structures that are so important for regions where you can't get to high ground easily, and there aren't tall buildings that are tsunami safe. So that's one factor. And then doing a lot of education as well. So both of these groups, the new Crescent Center, which is Cascadia Region Earthquake Science Center, there's the URL for that. And then the COPES Hub, which is Coasts and People addressing these things. COPES Hub has all these partnerships. And the one I just want to highlight is that there's a thing called the Cascadia Community Engaged Research Clearinghouse. This is where if a community or people from a community have questions that might be related to understanding better either chronic hazards like sea level rise and storms, or acute hazards like earthquakes and tsunamis, big land level changes, and so on that are associated with them, can hook up with scientists from the hub. And there's a website you can go to if you just find that Cascadia COPES Hub or the CCERC, you'll find it, and then connecting back to some of the hub researchers. So that's I think an important piece of this that we're doing. By the way, all of this is with National Science Foundation funding. Another thing that both of those groups are helping support that I'm especially excited about at UW is that some of our students, our PhD students, advanced graduate students, are spearheading a group, and especially a student of mine, I'm her advisor, Maddie Lucas here, has been working with the Quileute Tribal School in La Push to do a kind of a scientific exchange and seismometers in schools program out there at the school. So they started this really with the first push of some geological education in 2022, and now they've been back twice in 23 and this past spring in 2024. I don't have time to really give you do it justice, but one of the things I love about this program is it's really designed as a two-way exchange. So UW students go spend time teaching geology and earthquake science in the school, and as you'll see, establishing the seismometers. They also talk about what it's like being a student, and I should say both undergrads and grad students are involved in this, so they do some mentoring. They also are learning from the tribal members, both the kids and elders, a lot about, and there's a sort of explicit part of this that is about learning the language. They've been taking language classes. They've been learning cultural traditions like basket weaving and other things, and doing this culture and science exchange. And they've been out in La Push, and the students are coming to UW for, kind of campus visits and to try to understand what it's like to go be a college student and maybe a STEM student in particular. So there's Maddie and two of the other students teaching in the school, talking about the Cascadia Subduction Zone. And then, students at the school getting involved in these earthquake engineering projects, labs with a sort of little DIY shake table, a thing you can shake back and forth and see how strong your structure is, just as an example. And then they established what we call a citizen science seismometer. There's this type of seismometer, you see a picture of it down here, called a raspberry shake. And they don't cost much, a few $100s to maybe a little less than 1,000 for the really deluxe ones. We've established one, or the students, our students and the tribal school students established the first one out here on the coast, have been recording earthquakes at this spot. It's mainly kind of an outreach tool, but it enhances our seismic network in the region. We use a sort of, at PNSN, we have a little bit more sensitive and high grade of instrument, but these raspberry shakes are amazing. And clearly there's some that have been installed in PA and SQUIM, and I don't know why there's none in Port Townsend, but there should be. So that's a kind of a great factor of all this thing. Okay, another thing that we've been doing is actually trying to do new mapping. And this is the thing that made the news a few months ago, when we were looking at all of our work with ships, creating new maps and new sub-bottom imaging, so imaging down below the seafloor to try to map out these faults. Knowing what the Cascadia Subduction Zone looks like is not an easy thing. It's under miles of water, literally. It's all in the deep water. The shelf is up here, but all of this is really the deep water ocean. And all of these lines are track lines of new surveys we've done to try to understand where the faults are and how that large fault that runs the full length, which is this colored thing here, might be broken up into kind of segments. One of the big questions is, how likely is the truly full margin break all the way from Vancouver to Northern California versus one that breaks up into different pieces, and we call segmented earthquakes. The answer from this study is new evidence that big subduction fault actually is probably broken in a few places, or at least potentially is broken in a few places. And so there's some real evidence that maybe we have more of a northern Cascadia and a southern Cascadia segment that are broken along this line here, more or less, as well as a Vancouver Island segment. So in a way, that's the good news, that it might mean that we have likely several different breaks along the Cascadia Subduction Zone and not just one. But I have to say also, maybe the bad news part of it is, very clearly the largest part that's the most locked up and still capable of that magnitude 9 earthquake is this middle segment we call the Washington segment. And that doesn't really change our hazard here in coastal Washington at all. This is the source potentially for the largest, whereas the southern and the northern bits might have separate and somewhat smaller earthquakes, still with tsunami potential, but not at the same scale. So we're sitting kind of in the bullseye zone, I'm afraid to say, in Western Washington. And the Cascadia Subduction Zone, as I said, comes onshore just here in the Olympic Peninsula and sits mostly offshore, actually, elsewhere. We're also studying the potential for these things called splay faults. Those are branching faults that push up the surface more closer to the shore. This one's a good news story. A new study that we're just getting published now suggests that instead of one long one of these splay faults, which is actually part of the state's so-called L1 scenario, the one they use for all the tsunami inundation modeling, there's actually not very good evidence that that's a long extended fault. I'll spare you the details, but it kind of suggests that scenario we may be able to downplay a little bit in future kind of estimations of the hazard and still have a tsunami hazard, but not from one that's quite as close to the coast, which might change the time from earthquake to tsunami by a few minutes even. So that's emerging work. All right, I think I'm now pushing past my time limit, which I was afraid I would do, but I have just like two three more pictures that I'll show you. And this is this work we're doing trying to link ancient faults and places where that fault we can't get to in the offshore has an equivalent, but from a few million years ago, that's actually been pushed up, eroded off, and exposed high in the mountains in Olympic National Park. And I'm sitting there contemplating this zone that every one of these little sort of lines in the landscape, when we get down and really study the geology of them, turns out to be kind of a break, and all of it put together to find something we would call a fault zone. They have some width to them, a few hundred yards, actually closer to, it's like a quarter mile across this thing in this case, and with many what we would call fault strands that we think is a fossil version of the subduction plate fault that's down below our feet and down below the ocean now. And by studying the geology of a fault like this, we can learn a lot of clues about the conditions under which earthquake slip actually happens. Finding this thing was quite an adventure. This is the White Glacier. If you know the Olympic Park at all, that's Mount Tom. Mount Olympus is off to this side, just a little further away, actually back behind there. And this is an area called Lakes of the Gods that almost no one has seen. Probably you haven't seen this view of Olympic Park because not many people have. I was studying the old geologic maps made way back in the 1970s and recognized they had mapped some faults that no one had looked at literally since the early 1970s. So we went into this area right in here, which from a vantage point up near Mount Olympus looks like this. Same spot that the other picture was in. And so we went in there and really, we had to take a helicopter in order to get there and go through all the permitting process with the Park Service because hiking in for a field campaign just wasn't viable. We've spent a few weeks in this area really poring over the rocks, and now we're doing a lot of laboratory analyses on samples from that. And I'll just close with my last thought that the next frontier is really taking our seismic networks offshore. We have all of these monitoring systems. We know our biggest fault is the offshore, and we have very little to study it. There are some seafloor cables, big fiber optic and power cables. The Canadians have one, and the US has one, but down off the coast of Oregon. And we can put new instruments. And in fact, we are putting new instruments so we have more seismometers. We have seismometers on the seafloor with data streaming in real time to augment our on-land network and detect what's happening offshore better, including the possibility, at least, of precursory signals to, a potential future earthquake. We can't predict earthquakes. All we can do is forecast them, but we can study things that may help us learn whether we'll be able to make better predictions and better forecasts in the future. And that's our science cables. There are also lots and lots of commercial cables, and we would love to be able to actually use them for instruments. That's ongoing kind of discussion and negotiation. And maybe the next frontier is all these cables that carry our internet and carry our voice communications and everything else that crisscross the Cascadia subduction zone. But the cable owners have to have buy-in to this, and that's a big question. Okay, so I ran past what I promised to do. I'm sorry about that, but I'm very happy to take questions on anything I talked about or really anything related to earthquakes and tsunami hazards. Thanks a lot.
Thank you. Thank you so much, Harold. So we do have some questions in the chat. John, Paul, Kai, and Roy each put in questions. We only have 5 minutes left. So if you'll make it quick, John, do you want to ask your question about bridge?
Yeah, all I was asking is Hood Canal, what's the percentage of the bridge there being at fault?
Yeah, I can't answer it. I don't know the answer. The structural engineers probably have a handle. In fact, my colleague Mark Eberhard at UW is a real bridge construction expert and has assessed the hazards associated with, essentially, they've inventoried bridges everywhere. I'm afraid I don't have the answer to that for you, though.
Kai, you had a question?
Yes, my question relates to the likely non-tsunami damage here on the Olympic Peninsula. If we have a Cascadia subduction earthquake that's, I don't know, 100 miles off, the epicenter is 100 miles offshore, is there some way to come up with an equivalence, what the magnitude equivalent were of an earthquake with the epicenter right under Port Angeles, of just the shaking, not the tsunami effect? or is that too difficult to even estimate?
No, it is possible. And some of the work in that actually Cascadia COPES Hub is a group that is creating computer models of ground shaking for different scenario earthquakes. And the short version of the answer is the earthquake is very, very large from offshore, but proportionately, the shaking may not be worse than a closer in earthquake on something like that Lake Creek fault. I see the shaking from the crustal faults, like the Seattle fault, like the other ones that I mentioned, as the highest direct hazard to, collapsing buildings and things like that. The offshore fault, I mean, I don't want to minimize it. Certainly, building inventory in Port Angeles, in other communities along the straits, there's going to be very strong shaking that lasts for a very prolonged time of several minutes in a magnitude 9 sized earthquake. And the shaking damage will be potentially substantial, but it is advantageous that it's further away and that it comes from offshore of the actual Pacific, the open ocean side shoreline. The communities on the outer coast mostly don't have as many older or taller buildings. I can't say that's obviously 100% the case, but that's helpful as well. So, all other things being equal, again, it always depends on the magnitude, but closer in and crustal earthquake is going to shake harder and higher frequency, which is more damaging to those kind of structures than the big one in the subduction zone. I really see the subduction zone's greatest hazard is the tsunami.
So as far as outside the tsunami zone, can one say, it's likely to be similar to the Nisqually earthquake as far as structural damage goes, what you need to design buildings for to be able to withstand, not to fall down on people's heads, or twice as bad or half as bad, or is that too hard to do as far as planning for building resilience and things like that?
Yeah, it's a little hard to put as fine a point on it as that, because it depends on position, where we're talking about west to east and so on. Overall, I would say no, worse than Nisqually. Let's say we're talking about Port Angeles, but maybe not the sort of 100% devastation that people imagine, because we've seen the ground shaking from these big subduction earthquakes around the world, and the shaking intensity is often, not the full story. So I should just back up and say building codes, I think, are appropriately designed for the level of shaking we anticipate, but not everything is built to code. Older buildings are not, obviously, and we have to think about, what are all the other points of resiliency, the sewer systems, gas lines, water distribution, and so on as well. Damn.
Thank you.
All right. Well, we don't have natural gas out here, so that maybe is a blessing. Paul, let's do this one last question. What can we do more of in terms of public policy to better prepare for earthquakes?
Yeah, I see a couple of things. I'll say first, an overarching level is that when we think about earthquakes, an awful lot of our public policy is designed around what I would call life safety planning. That means we want buildings that won't kill people in earthquakes. That's obviously very good. We do want that. But we can think beyond that. And what we really need to think about, I think, is resilience and recovery, potential. How we can have a building that doesn't collapse, but also is unusable after the earthquake. And in fact, that's what the present day codes say you have to build. That's the standard you build to. You may have a building that you have to knock down, after the earthquake occurs, and that still sort of meets the standard that the code is designed for. I think a functional recovery is the term that gets used for construction, is a much better standard. And it turns out that, certainly there's the potential for greater cost during, upfront cost, but it's not as much more as you would think. Studies in different parts of the world, in Los Angeles than here, have suggested anywhere from a few percent to up to 5 to 10% change in the cost of construction for true functional resilience in new buildings. So that's one. And I think obviously the most important is redoubling our efforts on the old buildings that we know are unsafe, and old bridges and other things. So it's retrofitting or replacement. Schools, other structures, old unreinforced masonry buildings need to have the fixes addressed. It's expensive. There's not obviously necessarily funds for everything. I'd love to see the state taking this a little bit more seriously. We know our state has lots of demands on its budget, and it's not easy. And the federal government as well. Another policy area is that FEMA can, and they have moved in this direction, can put more and more into pre-disaster, resilience spending as opposed to just recovery spending. I could go on for a long time, but those are kind of key points.
Great. And then how do we sign up for ShakeAlert?
ShakeAlert, yeah. Okay, so ShakeAlert, you don't have to sign up as long as you get, let's say, Amber Alerts on your phone and you haven't turned them off, then you would get ShakeAlerts for the largest events. There is a second level. Oh, and if you have an Android phone, it turns out they've also built the alerts as a separate alert, not just the Amber style alert, the sort of federal government alert, but one that Android has designed into their operating system. So it will do. There was a screenshot in there for that. For some reason, Apple hasn't chosen to do that yet for iPhones. But there's an app you can download called MyShake. Just look for MyShake in the App Store, and you can add that to your phone. And what that does is that can alert for a little bit lower magnitude. So maybe one that isn't as likely to be damaging, but you're going to feel the earthquake. Maybe it'd be nice to get the alert. A lot of people feel that way. And so MyShake is sort of another layer on top of the universal ones.
Wonderful. All right. Well, thank you so much. It's 9:03, so we're going to call it a morning. Thank you so much for joining us. And Professor Tobin, thank you for your presentation. It was fascinating and very informative, very needed. Thank you.
All right. Thank you so much. I appreciate it. And you guys all have a great day.
Great. Bye-bye.
Thank you.